Various different methodologies can be used to measure the transmission rate of permeants through a polymeric material. Isostatic, quasi-isostatic, and gravimetric techniques are three popular techniques used in packaging applications. Isostatic and quasi-isostatic methodologies differ in the way the gas flow is maintained on the carrier gas side. In the gravimetric technique, weight gain or weight loss is measured as a function of time. Let's have a look at isostatic procedure first. In such technologies, permeant vapors flow continuously through high concentration cell chamber and an inert carrier gas flows through the low concentration cell chamber. A film is sandwiched in a two-part permeation test cell. The film separates permeant side and the carrier side. In the isostatic permeability technique, constant pressure differential is maintained between the two sides throughout the measurement. The permeant CO2 gas in this example flowing on the bottom side is maintained at constant pressure P2 at temperature T, and the other side is constantly flushed with inert nitrogen gas. As negligible or zero CO2 molecules are present on the top side, so top side has zero permeant pressure. Generally, zero vapor pressure of the permeant is maintained on the carrier side in isostatic techniques. The CO2 molecules adsorb, diffuse, and then desorb towards the carrier side. Once the molecules desorb and enter the carrier side, they are instantly flushed with the nitrogen gas and carried to the sensor or the detector. Sensor quickly measures the amount of the permeant molecules moved to the carrier side as a function of time. Initially, there is a lag, and at the start of the test, less number of permeant molecules transmit to the other side. Such a state is called unsteady state. After a period of time, the number of molecules diffusing through the polymer film and desorbing on the other side of the film becomes consistent. Such a state is called steady state. The transmission rate numbers obtained in the steady state are converted into the permeability coefficient. The transmission rate numbers can change with varying thicknesses of the polymeric film and the change in the pressure difference between the permeant side and the carrier side. To normalize for the thickness and to account the pressure differential between the two sides, the permeability coefficient is calculated. For calculating the permeability coefficient, the transmission rate numbers are multiplied with the thickness and divided by the pressure differential between the permeant side and the carrier side.